But first and foremost, we're going to go back to circular functions. We're going to look at some trig. We're going to say, first thing we learned when we started studying trig, I'm sure, was degrees to radians, how to convert those. And we learned that special angles, we know that a 60-degree angle is actually pi over 3 radians. And we know that a 30-degree angle is actually pi over 6 radians. I always remembered that by making sure that 30 degrees was the opposite of that pi over 3, the 60 degrees and the pi over 6, how they did not necessarily match up. Right? They were the other ones. If we redefine our trig definitions in general, our sine, cosine, tangent, with respect to the circle, right? If it were a unit circle, we know that sine is my y-coordinate, cosine is my x-coordinate. But in general, we can say that too about even with radius r, I can say that my sine is my y over r, cosine is x over r, and tangent, of course, is sine over cosine is y over x. Notice the r's cancel, or just that y over x coordinate. We're going to define some more trig functions. There are actually 6 trigonometric functions. And so we're going to talk about those other 3 that are not covered in the IB Math SL curriculum, but they are important for anyone who studied pre-calculus, anyone going on to college math. Right? So the first one we're going to define, these terms are called secant, cosecant, and cotangent. They're actually known as the reciprocal trigonometric functions, and we'll see why here in a minute as we define them. First, I'm going to start with the secant. The secant is defined as 1 over the cosine. Now this is why I brought up earlier that pi over 3 radians is 60 degrees, pi over 6 radians is 30 degrees. Because the secant doesn't map with the sine. It's kind of the opposite is what I would think. It's that counterintuitive idea that secant goes with cosine. And as you can probably guess, cosecant goes with sine, right? So they are reciprocals of them. The reciprocal of the cosine is the secant, reciprocal of the sine is the cosecant, and as you've guessed, I'm sure, with only the tangent left, the reciprocal of the tangent is known as the cotangent. Instead of sine over cosine, it's cosine over sine. Right, so using those 3 trig definitions, we're going to translate these definitions in terms of y and x. So if secant is the reciprocal of cosine, the reciprocal of this is r over x. The secant is the reciprocal of sine, which of course is r over y. And the cotangent, again, is my reciprocal of the tangent function, so x over y. And so we're going to be using these definitions, combination of these definitions and just that simply that idea of reciprocal to be able to talk about these 6 trigonometric functions of various angles. Now we are going to have our unit circles, which is rather nice, that I can find the exact value of all my trigonometric functions here. So if I pick cosecant, for example, cosecant we know is the reciprocal of the sine function. I'm going to be looking at my y-coordinate. But first and foremost, I actually have to find my angle. Now 2 pi divided by 3 is smaller than pi, so it's up here. 2 pi, there it is. 2 pi divided by 3. Right, and I keep that and I say, well, my cosecant says flip the sign, right? Reciprocal of sine. Now, since my sine is radical 3 over 2, my y-coordinate, my cosecant is going to be, flip that, 2 over radical 3. Now, of course, I could rationalize that, but I don't need to. I'm going to say that's fine without rationalizing it, because by rationalizing it, it's kind of messier. It's 2 radical 3 over 3. So it's a little more things to write. So I'm going to go ahead and leave that as 2 divided by the square root of 3. I'm going to pick a new angle. I'm going to say now I'm looking at 5 pi over 4. So that's more than pi. 5 pi over 4. Ta-da! Now I want the secant. Now the secant is the reciprocal of, remember, secant matches to cosine. So 1 over cosine, 1 over my x-coordinate. My reciprocal here, notice this does say square root of 2 over 2, but if we recall, it's also known as just 1 over radical 2. Right? 1 over radical 2. So its reciprocal is going to be negative radical 2. If you notice as well, I could just take the reciprocal there, negative 2 divided by radical 2, and then I would rationalize that. Because it will simplify a lot, by rationalizing it, I'm going to ask to be simplified as that negative radical 2. We've taken a look at cosecant and secant. Now let's look at cotangent, which again is going to be the reciprocal of the tangent. So I go to pi over 4, pi over 4, cotangent, instead of y over x is x over y, but because it's that pi over 4, that 45-degree triangle, right, it's the same thing. That's just going to be simply 1. 1 divided by 1 is still 1. My cosecant of 7 pi over 4. So I find 7 pi over 4, which is almost 8 pi over 4, or 2 pi. So 7 pi over 4 is lying right over here. I say cosecant. Well, cosecant is the reciprocal of the sine function, so my y-coordinate. Again, the reciprocal of this is going to be just that radical 2. Notice it's my sine function, so it still is negative down in this quadrant. So I get negative radical 2. And finally, the secant of 5 pi over 6. 5 pi over 6 is right here. The secant is the reciprocal of my cosine, so my x-coordinate. Take the reciprocal of that, I keep my negative sign, and I've got 2 over radical 3. So if you remember, really I have in this first quadrant, all my terms are positive. I have positive x's, positive y's. All 6 of my trig functions are positive. In this quadrant 2, my x-coordinates are negative, which means my cosines are negative. That also tells me my secants are negative. Cosine is just the reciprocal of secant. My sines are positive, which means my cosecants are positive. Now tangent, sine over cosine, so that's negative, so is cotangent. I move to quadrant 3, I've got negative x's and negative y's. Right, so my sines, my cosines, my secants, my cosecants are all negative, but if I divide by a negative, I get a positive number. My tangent and my cotangent are both going to be positive down in quadrant 3. So I can double check if I ever have to find those. And finally, quadrant 4, I have positive x's, so positive cosines and positive secants. And I have negative y's, so negative sines and negative cosecants. And of course, negative divided by a positive is a negative. I have negative tangents and negative cotangents in my various quantities. So I know that these values are true. I can also simplify, and just to make sure that it's not too crazy finding these tangents or cotangents. Right? A number divided by itself is simply 1. If I do 1/2 and divide it by radical 3 over 2, we're dividing by a fraction and multiplying by the reciprocal. That's going to simplify to 1 over radical 3. Finding the tangent of pi over 3 is radical 3 over 2 divided by 1/2. Just going to simplify to radical 3. Of course, 0 divided by 1 is 0, and as we know, I hope that we all know, that 1 divided by 0 is undefined. The tangent does not exist up here. Right? Cotangent is the reciprocal of those, which again is going to be 0. It's going to be 1 over radical 3. It's going to be 1, radical 3, and undefined. Even my secants and my cosecants are not such scary numbers. The reciprocal of these values, the reciprocal of 1/2 is simply 2. The reciprocal of radical 3 over 2, I'm fine with you leaving as 2 over radical 3. Now the reciprocal of radical 2 over 2 is the kind of special one, right? It is a little tricky when I'm simplifying it, but he's just simply radical 2. Right, so I shouldn't get too crazy of numbers for these special triangles, these special angles with any of my 6 trigonometric definitions for my functions here. Alrighty folks, we're going to go through an example here. Find the values of all six trigonometric functions given that the sine of theta is 2/5. Now if I know the sine of theta is 2/5, that's not quite enough information because I'm not really sure which quadrant that is. Some of the values might be positive or negative until I say where. I say theta is between pi over 2 and pi, right? So if it's just positive, I know it could be either of these first 2 quadrants. Now I've given you this restriction, which means between pi over 2 and pi, so we're over here in this quadrant. Right? So I'm going to draw my line over in that quadrant, knowing that I'm talking about this angle. Now if I drop a perpendicular there, now I can think of a circle around here with a radius r and a height of y and a width of x there, and I know that sine is y over r, or knowing that it's opposite over the radius there, the hypotenuse, and say 2/5 y over r, right, is this sine of theta. I go, wait, I can probably find this leg as well. My good friend Pythagoras says x squared plus 2 squared equals 5 squared. Solving this here, I could get x is positive or negative square root of 21. However, I know which quadrant I'm in, and in this quadrant my x coordinates, of course, are all negative, so I can say negative radical 21. So I'm going to find my trig functions. Notice how I wrote these. Sine, cosine, tangent, which is what we're used to, but notice that I put sine, cosecant, I put cosine, secant, and tangent, cotangent. I put the reciprocals next to each other so I could see that clearly and not do too much work to find these once I get this first column done. So as we know, sine's already there. It's going to be this y over r. Cosine is x over r. Tangent is y over x. All right, so I get 2/5 x negative radical 21 over r. 2 over negative 20 radical 21, but notice I can put that negative upstairs or downstairs. It doesn't really matter. I can put it in front if I want to. Typically it's either seen in the numerator or out front, so that's why I have it written here. Again, as long as one of them is, the tangent itself is negative, I don't care where I put it. Now my reciprocal trig functions are pretty straightforward. I take my 2/5, I flip it. My negative radical 21 over 5, and I flip it. Again, with the negative, I keep it upstairs just out of habit. Cotangent, I just flip it, negative radical 21 over 2. Now I could use the same thing. I could use my r over y, my r over x, and my x over y here. Either way, these work if I just take the reciprocals directly from here or just use those functions I've defined earlier. We should look at another example. Again, the 6 trig functions given the secant. Ooh, what's secant? Keeping in mind though, now I say here's my other restriction, my second restriction, excuse me. My second restriction. And keeping in mind the cosine is 1/5, right? Cosine means reciprocal of secant. Secant is reciprocal of cosine. Again, I know that means that the cosine is positive. So I'm thinking quadrant-wise. Cosine or secant are positive. I'm over here, my x's. Where sine is negative, I'm down here, right? I need to know where both of these are true. So clearly they overlap in this fourth quadrant. That's the quadrant I'm going to draw my little line in. I'm going to draw my perpendicular. So I'm going to get rid of those little extra shading there so I know which quadrant I'm in. Again, secant tells me that's positive, tells me on this right side, quads 1 and 4. Sine's negative tells me this downstairs, quads 3 and 4. Both of those are true in quad 4. If I know the secant is 5 over 1, my radius must be 5, my x is 1. Or again, I could see it here. I could flip that, took the reciprocal. X is 1, r is 5. Right, and again, Pythagoras is a great guy. He lets me find this. 25 minus 1 is 24. Again, I can break down this radical, though. I can see a 4 and a 6 in there. I get plus or minus 2 radical 6. But again, I'm dealing with a specific quadrant. In this specific quadrant, all my y values are negative. So I get negative 2 radical 6. Again, with my sine functions, cosines, and so on. Again, I mapped sine to cosecant. I mapped cosine to secant. I mapped tangent to cotangent. Just so when I see this, again, opposite over hypotenuse. Again, y over r. Either way I think of it. Y, negative 2 radical 6 over r5. Cosine's kind of given to me, right? It's given the reciprocal here. And tangent, of course, is y over x, but negative 2 radical 6 divided by 1. I said, let's just simplify that here. And I said my reciprocal functions, again, just flip them. Negative 5 over 2 radical 6. 5. Negative 1 over 2 radical 6. Right? Just reciprocal here. Whether I found them directly from these or whether I looked and said, okay, for cotangent, for example, is x over y. Again, out of habit notation, often seen in the numerator anyway. So these are my reciprocal trig functions. Pretty straightforward. The same idea as what we did in chapter 8 with my cosine, sine, and tangent itself. Now I'm just taking the reciprocal. The inverse trigonometric functions is actually something we've already seen before as well. It's got some fancy formulas. Inverse, again, sine to the -1 is often seen. Also called arc sine or arc sin is how it's denoted, right? Just like we write sin rather than sine. And it's defined by this fact, and we say the inverse sine of x equals y, if and only if the sine of y equals x. Well, what does that mean? If the sine of y equals x, I'm saying the sine of some angle equals this value. So really when I read this, I should really read the sine of what angle y gives me this value x. I say, well, let's think about it. What can be true of my domain and range? Well, my domain of the inverse is always my range of my initial function. Right? My domain of my inverse is always the range of my initial, and the range of my sine function we know is between -1 and 1. Now my range, in general, I know my range can keep going. My domain for my sine function was all real numbers, but I can't have a domain mapping to multiple range values. I can't have one x with multiple y's. It's not a function. It won't pass the vertical line test anymore. So I make a restriction. I say, well, what values can I have to make sure I get signs being positive, signs being negative just once? So I say I'm just going to put it from negative pi over 2 to pi over 2. I'm just going to look in that window. Because if I have, and that's really the first quadrant and the fourth quadrants. First quadrant signs positive, fourth quadrant signs negative. I am going to write as negative values here instead. Inverse cosine is very similar. Inverse cosine, also written in this same way. I'm still asking myself, the cosine of what angle gives me x? Right? The cosine of what angle gives me x is what I'm looking for. Same domain, just because I had the same range for sine and cosine, so I have the same domain for inverse sine and cosine. The range, though, is different. If I kept that same range and I was looking at quads 1 and 4, the cosine's positive in both of those. So instead I'm going to define 1. I like that first quadrant. It's pretty straightforward. I'm going to put quadrants 1 and 2, right? So those top half of my circle from 0 to pi. My tangent function, again, written that same way, saying the tangent of what angle will give me x, tangent of what angle gives me x, written either direction. My domain in this case really is going to be all real numbers, right? I can have tangent, it can be anything that I want. If I recall, the tangent function is one of those that shoots off to infinity. So its range was all real numbers. Now its domain is all real numbers. My range, though, to make sure that I only count each angle once, I'm going to say it's between negative pi over 2 and pi over 2. Again, same as that sine function. So if I'm looking on the unit circle, that's really what I ask. Rather than saying arc sine or inverse sine of negative radical 3 over 2, I'm going to ask myself what angle has a sine of radical 3 over 2. So sine of radical 3 over 2, negative radical 3 over 2, negative here. And I find it down here. Now on my unit circle, it's written as 5 pi over 3. I need to call it negative pi over 3. Same denominators are going to match up. I'm just going to make all of these instead of 3 pi over 2, negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, right, to make sure that they're in this range. So this is simply going to be 5 pi over 3. The inverse cosine of radical 2 over 2. Instead of reading it that way, I like to read it as what angle has a cosine of radical 2 over 2. Now I know to look right here and I can say, well, that must be pi over 4. Again, instead of reading an inverse tangent of 0, I'm going to say what angle has a tangent of 0. And tangent is sine over cosine, so tangent is y over x. 0 divided by 1 gives me 0, so that's just going to be 0. Again, I have to call it 0. I can't call it 2 pi because 2 pi is not between negative pi over 2 and pi over 2. So I have to say 0 here. Wait, inverse sine of 2. What angle gives me a sine of 2? This is when you should go, Miss Mickle, of course, there's no such angle. This must be undefined, right? One of our favorite words in mathematics. We don't know what to write, so we just write it undefined, right? It doesn't make sense. That's why it says if it is defined. And if I say what angle has a sine of 0, well, of course I'm coming over to that same 0. Again, not 2 pi, but that 0 value. These are nice special angles, but again, I might not have special angles, and you're like, whew, that looks crazy. The exact value of each expression, again, if it's defined. Well, the cosine of the arctangent of 12 over 5. Whew. If I just ignore this cosine at first and I say, well, what angle has a tangent of 12/5? Well, let's draw that out. Let's draw that out. I know the tangent only exists here, the inverse tangent's only in these two quadrants. And if tangent's positive, again, it must be that top quadrant. And if it has a tangent of 12 over 5, that must be y over x, 12 over 5. I still don't know what to call this angle, but at least I know those hold true. And if I know these to be true, 5 squared plus 12 squared equals 169. All right, and I can say the square root of that. That gives me a radius of 13. Even though I don't know what this angle really is, the cosine of this angle is still going to be x over r. It's still going to be, this should say 5 over 13. Excuse me, this should be incorrect. This should be 5 over 13 x over r. So ignore this answer. Should be 5/13. I say, let's look at a new problem. I say, well, what's the cosecant of the inverse cosine or arc cosine of 3/7? Again, I don't really know what angle this is. This is some angle, but I do know some things about this angle. I know it would have to be in one of these first two quadrants, but I know since it's positive, it's in the first quadrant. Whatever angle has a cosine of 3/7 means x must be 3, radius must be 7. Again, my good friend Pythagoras can figure out that this next side is 2 radical 10. And if I want the cosecant is the reciprocal of sine. The reciprocal of sine says radius over y, 7 over 2 radical 10. And so 7 over 2 radical 10. Even though I don't know the angle, I can figure out which values go where. And again, use my trig relationships, all those x over r's, r's over y's, things like that. Finally, I get to this last one. I say, what's the sine of the inverse sine of x? Well, the inverse sine of x is some angle such that it has a sine of x. Whatever that angle is, if it has a sine of x, then the sine of that angle must itself be x. Right, so that's pretty straightforward in this case. Right, so it's pretty straightforward here in this case. So those are our examples of inverse trigonometric functions. Again, that undoing fact here. So I hope that helped. You can work on your worksheet. Again, I will answer more and more questions as you continue to come to class. We have all of next week until Thursday to make sure that we're masters of this subject.